W7, Refraction of Light. The lessons we've done so far, W1 to W6, have been about waves generally. So we have included a few light waves in those lessons, but from here on we're just going to think about light. So we can also call this section optics. So we're going to start off with refraction, and in the photograph, you have a look closely, you can see a polar bear here leaning on the rock, and his head is over here. Now that's not photoshopped, that's a genuine photograph, and the effect is caused by refraction, which is what we're going to look at over the next couple of lessons. So before we look at that in more detail, I'll just mention the fact that we can, when we're describing how waves travel, we can think about wavefronts or about rays. So with water waves, we're used to, it's quite easy to think about sort of a high point of a wave travelling, and we're actually then looking at wavefronts. With light, remember that it's a transverse wave, so it's sort of wiggling up and down as it goes, and this would be the direction of the ray from a ray box. But occasionally we can think about wavefronts as well, but they're always perpendicular to the direction of travel. Okay, so refraction. Snell was a physicist who looked at the way light travels as it goes into different materials. So let's assume in this diagram we've got some air up here and something here which could be glass or water. Well, let's assume it's glass for now. So what Snell found was when he shone a ray of light into the glass block and measured the angles, so the angle going in he called the angle of incidence, and the angle after it had gone into the block was called the angle of refraction. And he found that when he plotted on a graph the sine of I against the sine of R, he got a straight line. And the gradient of that straight line he gave the symbol N, which stood for the refractive index, because he found that different materials gave a different slope here. So the gradient N was characteristic of the material. So in this diagram, the refractive index of the material, N, M for material, is equal to the sine I, sine of the angle of incidence, over the sine R, sine of the angle of refraction. So that is the gradient of this graph. Now light is actually reversible, so a more practical way of phrasing the equation comes from this bit here. So let's draw the diagram again. We've got a ray going in and a ray going through the glass. So rather than calling it I and R, let's call it θ1 and θ2. And the reason for doing this is that light is entirely reversible. So if you started here and shone the light in this direction, it would follow exactly the same path. So it's less confusing if we just label them with 1 and 2. So the idea is that θ1 is the angle in material 1 and θ2 is the angle in material 2, and that's easy to remember. So Snell's law can be rewritten like this: N1 sine θ1 equals N2 sine θ2. And that's fairly easy to remember because we've got the 1's on the same side and the 2's on the same side as well. So material 1, material 2. And that's how it is in the formula book that you'll get in your exams. So there's the equation again: N1 sine θ1 equals N2 sine θ2. Now, a special case is if one of those materials happens to be a vacuum or air, and in that case the refractive index is actually 1. So if we put n equals 1 into the equation here, we can rewrite it, make n2 the subject, and we get N2 is sine theta 1 over sine theta 2. And that's actually the same as the original version of Snell's law, which was sine I over sine R. Okay, but this version we can derive directly from the version on the formula sheet. So just to make sure we've got what everything means here. N2 is the refractive material index of the material, 2 standing for the material. Theta 1 is the angle in air, because the air is material 1, and theta 2 is the angle in the material. So we've got sine theta 1 over sine theta 2, which is exactly the same as saying sine I over sine R, but we don't have to measure, it doesn't matter which direction the light is travelling in.